Hello, in this video, we're going to take a look at a couple more examples of improper integrals and how they work, specifically the type 1 improper integrals. So we are going to take a look at this example here first of the integral from negative infinity to 0 of e to the 2x dx. First thing, at any point, if we see a bound of infinity, we want to switch that bound out for a limit. So we're going to do the limit as t goes to negative infinity of the integral of t to 0 e to the 2x dx. Now I can evaluate this integral just fine. We know that this integral will work out to be, with a very basic u sub, keeping our limit, this integral is 1/2 e to the 2x, evaluated from t to 0. Plugging in our bounds, our upper bound of 0, we have 1/2 e to the 2 times 0, minus 1/2 e to the 2t. E to the 0 is 1. So 1/2 times 1, minus our limit as t goes to negative infinity, 1/2 e to the 2t. Now, as t goes to negative infinity, that will make this exponent here negative. And it will also make the exponent increase it. So this exponent is going to become a really big negative number. E to a really big negative number gets closer and closer to 0. So the limit as t goes to negative infinity of e to the 2t is 0. 1/2 minus 0 is 1/2, meaning our integral from negative infinity to 0 of e to the 2x dx converges to 1/2. Let's take a look at another example. We have the integral from negative infinity to infinity of x squared over x to the 6th plus 1 dx. First things first, some immediate substitutions is we have a bound of infinity in both the lower bound and the upper bound. This means we're going to have two limits. We're going to have the limit as t goes to negative infinity of our lower bound to some number. We can really use any number. 0 often is going to be the best, but we can pick any number. I'm going to pick 0. Of x squared over x to the 6th plus 1 dx. So there's one piece of our interval, and then we need the upper bound to be a limit. And so we're going to take a different variable and have z to infinity of 0, picking up where our lower bound left off, or our upper bound technically left off. And we have the same integral again. Since we have the same integral both times, this part, we just need to figure out how do I find an antiderivative of x squared over x to the 6th plus 1. Technically, we could try and do partial fraction decomposition, but this is actually a u sub problem if we identify the fact that x to the 6th is x cubed squared. And making u equal x cubed, du equals 3x squared dx, or 1/3 du equals x squared dx. So going to use this u sub was limit as t goes to negative infinity. We need to plug the bounds in. So when our bound is a variable, that's just as easy as plugging it in, and t plugged into x, well, x cubed means our lower bound becomes t cubed. Our upper bound, when we plug 0 into x cubed, is still going to be 0. I'm going to write it as 0 cubed to demonstrate we have changed our bound, but in this case, the bound will stay the same. It will stay 0. And now the numerator becomes the 1/3 du. And we have times 1 over u squared plus 1. Repeat that for our second integral. Again, we've plugged 0 in, so 0 cubed is 0, and z cubed. And we once again have 1/3 1 over u squared plus 1 du. Since we have a 1/3 over, since we have a 1/3 in both these integrals, I'm going to pull that all the way out to the front to ignore it, because it's on both of these. Now, the antiderivative of 1 over u squared plus 1 is arctangent, meaning we're looking at the limit as t goes to negative infinity of arctangent of u from t cubed to 0 cubed, plus the limit as z goes to infinity of arctan of u from 0 cubed to z cubed. Plugging in those bounds, and zoom in. Plugging in the bounds, we get 1/3 upper bound first, arctan of 0 cubed. And again, 0 cubed is 0, so I'm just going to leave that as a 0 this time. Minus the limit as t goes to negative infinity of arctan of t cubed. Plus the limit as z goes to infinity of arctan of z cubed minus arctan of 0 cubed, which is 0. Arctangent of 0, as a reminder, I'm going to go off to the side. Arctangent's graph looks like this, where this lower asymptote is negative pi over 2, and this upper asymptote is a positive pi over 2. And at 0, we cross the x-axis. So arctan of 0 equals 0. The limit as t goes to infinity of arctan of t equals pi over 2, and the limit as t goes to negative infinity of arctan of t equals negative pi over 2. Gonna make that negative a different color just to point out that's not a dash anymore. Make that red instead. There we go. So those are all of our limits we need. while we evaluate this. So arctan of 0, we said is 0. So this canceled and this canceled. And if we had picked any other number, if you notice, I said we just need to pick some number to break it up. 0 is often the most convenient. But if I had picked 1, I'd have arctan of 1 minus arctan of 1. They can cancel each other. We need to break it up to have the two limits. But if the antiderivative is worked correctly, they should be canceling each other out. Now, the limit as t goes to negative infinity of arctan t cubed, if I cube a negative number, it is still negative. So negative a cubed is still a negative number. So this would be like we were still going to negative infinity. The cube does not suddenly make this positive. So we have 1/3 0 minus the limit of arctangent as t goes to negative infinity is negative pi over 2. Plus, now the limit as z goes to infinity of arctangent is the positive pi over 2. We have negative pi over 2. So we have pi over 2 plus pi over 2, which ultimately is pi. Pi times 1/3 is pi over 3. So, zooming out, this means our integral of negative infinity to infinity, x squared over x to the 6th plus 1 dx, converges to pi over 3. We get a finite area. So there are our examples for type 1 improper integrals. In the next video, we'll look at comparing some type 1 improper integrals.